Let's discuss the shapes of molecules. Here we have CO2. CO2 is composed of one carbon atom and two oxygen atoms. Here, the central atom is carbon. Here, oxygen atoms, they have 6 valence electrons. So they need 2 more valence electrons to be stable or happy. And they get the 2 valence electrons from this carbon atom in the center. So they form a double bond with carbon. After sharing these electrons, let's check the number of valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. So all of these atoms are stable. All of them now have 8 valence electrons. Now, we can simplify this electron dot structure by removing the valence electrons around the atoms on the sides of the molecule. So here we can simplify this one as like this. So this is the simplified electron dot structure for CO2. Now this one is the structure of CO2 on a flat paper. But of course, as we know, CO2 have 3D shape. They are not just flat. So we represent the 3D structure of CO2 or other molecules using the ball and stick model. Here, we use balls to represent the atoms, and the sticks will represent the bonds connecting the different atoms. Here, we have 3 atoms, so we also need 3 balls. So this will be the carbon atom, this will be the oxygens. And again, these atoms are bonded by these bonds over here, represented by the sticks. Now, what's the shape of CO2? Is it a linear shaped molecule or a bent shaped molecule? Or both? So CO2 can either have this one or it can either have this one. The answer is this one. So this is the only possible shape for CO2, and we'll discuss why. If we go back to the model, so again, these are the atoms, and here we have the bonds, right? So here we have the bonds, and what's in these bonds, by the way? So these bonds are occupied by electrons, right? Because here, these atoms are sharing electrons. Also electrons. So here, this is an electron group. Okay, we have a term for this, electron group, and also here another electron group. So these areas are occupied by electrons, and these areas are also negatively charged because again it's occupied by electron. Let's go back to our discussion on the charges and their interaction. So same charge repel each other. So we can expect that these electron groups are repelling or moving away from each other. What do you think will happen if we bring these electron groups closer to each other? Again, negative and also negative. So obviously they will repel because they have the same charge. So these electron groups would like to go to move as far from each other from the central atom. So we can see that here the most stable shape for CO2 is a linear shape. So that's 180 degrees from each other. So the shape for CO2 is a linear shape. Let's go to this one. What if we have 3 atoms? So here we have 3 electron groups. Again, these bonds are electrons or negative. So is this the most stable shape for this molecule considering the repulsion of these electron groups? Again, they would like to go as far from each other, so the most stable shape for this will be like this. So here they have equal distance from each other. So this is the shape for this molecule. Let's have SO2. So SO2 will have this structure. Okay, if you see here, this sulfur can actually, it can have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this sulfur is an example of an expanded octet. So some atoms can actually have more than or expanded octet. So it can have more than 8 valence electrons. We'll not go to the details of that. We'll just discuss the concept behind the shape of the molecules. Here we have SO2. So here we have 3 electron groups. We have this one, and this one, and also this one, because these are also electrons. So overall, we have 3 electron groups. So the shape for this SO2 will be, okay, first, this is the ball and stick model. Again, these are the electron groups. This one is this one, this one is this one, and this lone pair, okay, we call this as lone pair. Pair because it's obviously 2, and the lone because it's not shared to other atoms, so it's alone or lone. So here we have a 3 electron groups, 1, 2, 3, and in that 3 electron groups we have 1 lone pair. Again, considering the repulsion of these 3 electron groups, the shape will be like this. So the shape for SO2 is a bent molecule. Okay, it's a bent molecule because here we have a lone pair repelling with the other electron groups, or repelling with the bond of SO2. Okay, let's try to visualize CS2. Let's try CH4. That CH4 will have something like this: carbon, hydrogen, hydrogen, hydrogen. So hydrogen needs 1 more electron, so it will form a single bond with this carbon in the center. Let's check hydrogen 1, 2, happy 1, 2, 1, 2, 1, 2, carbon 1, 2, 3, 4, 5, 6, 7, 8. So this one is the Lewis dot structure, or the electron that structure. Next, let's go to the Vesper, or to the 3D shape of this molecule. We have a guide for this. So let's count the number of electron groups. That's 1, 2, 3, 4. So we have 4 electron groups, and here we don't have any lone pair. Here we can look on this guide, and we can see that 4 electron groups with 0 lone pair, the shape is tetrahedral. So here, this is carbon, this is hydrogen, and hydrogen here. So this line means it's on the plane, it's on the flat surface. This wedge line means that this bond is coming out to you, or it's going forward. And this one is going behind the paper, that's the H. So this is the shape for CH4. It's a tetrahedral shape. Let's see that one on the simulator. Again, that's 4 electron groups. So this is the shape for CH4. Let's try to draw this. Again, this is carbon, and here we have hydrogen and hydrogen. Again, it's on the plane, or it's on the flat surface. Then this bond is coming out, and again, to represent that, we draw a wedge line. Wedge. And this bond is going backward, so we use a broken line over here. So that's the structure for this CH4. It's tetrahedral. Okay, that's tetrahedral. That's the shape of a CH4 molecule.